We're going to start with a lecture of part one of David Stroop on Ekman pumping, vertical velocity, and ocean energetics.
Okay, thank you very much, and thanks to the organizers for inviting me here. I've had a great time meeting lots of people, and enjoyed the talks and posters and such. Last week we heard a lot about geostrophic turbulence and the near inertial wave field, and both are ultimately forced mainly by the winds at the surface. And the surface boundary layer includes a sort of not only the geostrophic bit and the inertial gravity wave bit, but also a frictionally balanced Ekman part of the flow. So that's what I'll be talking about today. And my background is sort of I'm a large-scale oceanographer, and gradually over the years I got more interested in the mesoscale and now the submesoscale. And I've thought a bit about energy transfers between geostrophic and wave modes and such. Sort of a theme of my research has been balancing the energy budget of the ocean. And as we've seen, geostrophic turbulence has this difficulty. It sort of lacks a robust transfer of energy towards dissipation scales. So if you want to get rid of the energy, you need, you need either the bottom boundary layer, which is also an Ekman layer, or maybe a leakage of energy into ageostrophic modes, which can cascade energy forward. But if I'm interested in balancing the energy budget, I should not only look at the sinks, but also the sources. And so that brings me to look at the surface boundary layer. So this energy input is, well, kind of U dot tau, where tau is the wind stress. And this is work with Jan's a postdoc. He's actually a postdoc funded mainly by Carolina Dufour, but we've sort of siphoned off a little bit of his time, more or less pro bono for this project. Louis-Philippe is a colleague of mine at UCAR. In most of atmospheric science, UCAR means, what is it, University Corporation for Atmospheric Research. In Quebec, it means University of Quebec at Rimouski. So Louis-Philippe's at Rimouski. And Victorine is finishing her master's thesis in the next week or two. And these are Thomas and Yanshu, our former students of mine. So two parts. I'll start out the first lecture is on linear Ekman theory, which is pretty simple. It just relates the vertical pumping velocity to the wind stress. And the only thing that's interesting really is that the wind stress depends on the surface currents. And that's been well known for a while, and it has consequences for the energy input to ocean circulation. And there was some work done, including by myself in the early 2000s, for example, and other people before. But it's back in the news, so to speak. People are running models now and think this effect is overrepresented. So that sort of is going to lead up to Victorine's master's project. And then the second part, I'll talk about what people call nonlinear Ekman theory. And for nonlinear Ekman theory, you assume that the stress is given, so it may or may not depend on the ocean surface velocity, and you worry about how the currents modify the relationship between the pumping velocity and the wind stress curl. And the surprising thing to me was that it agrees well with vertical velocities in what on a good day I might call mesoscale permitting models, or certainly eddy resolving GCMs, at least in the limit where there's no high frequency forcing, less so when there is high frequency forcing, and then that's where I'll wind up. And so here's an outline of my talk. I'll just, I was told it could be a pedagogical talk, so I'll maybe have a little bit too much at the beginning, but review here. And then I'll also review where we usually use a quadratic drag law to represent the stress, and that comes from boundary layer turbulence. And I won't go into the details of it, but I'll give a brief hint of where that comes from. The ocean velocity, ocean surface velocity dependence in the stress, I'll give a first look and sort of recent work, and then our current work. And then after the coffee break, I'll come into nonlinear Ekman theory. So there's some early work by Melvin Stern, and then there's Winograd and Thomas came up with a modification to this in streamwise coordinates about 6 or 8 years ago. And then we did a slab model. So we had like a 2-layer shallow water model with a slab layer embedded in the top layer. So I'll talk a little bit about that, and then go into this general circulation model with Jan and Louis-Philippe. And then lagniappe is I'm from Louisiana. Lagniappe's a word that means just a little something extra, like if you go to a store and the merchant gives you a piece of candy when you check out for the kids, some sort of worthless toy. It's just a little something extra at the end. And I'll just say a couple slides on sea ice, Arctic sea ice. There's still enough sea ice so that at least part of the year, the relevant stress is not the wind stress, but the ice to ocean stress. And you can have leads in the sea ice where you might have one flow going this way and another one going that way, kind of like a transform fault. And you might imagine that there's a near discontinuity then in the stress and very large Ekman-based Rossby numbers. So we get an asymmetry between anticyclonic forcing, for which you get a very sharp downwelling current, and cyclonic forcing, for which you don't, right? You don't get a focused current at all. Okay, so I'll just jump right into the linear Ekman theory. So here's my horizontal momentum equation. And I'm admitting that my U here is some sort of an average. They're small scale eddies, small scale turbulence, and here I'm just using a constant eddy viscosity. So AUZ is just the vertical transport of horizontal momentum by the unresolved eddies. And if I assume a small Rossby number and frequency Rossby number, then I get rid of this term, and I have this linear equation. And the kind of idea behind Ekman theory is that the geostrophic part of the flow, or the non-Ekman part of the flow, doesn't vary over the depth of the Ekman layer, which is 10 or 20 meters or so. So the UZZ term is really just d by dz, or Z2Z derivatives of U Ekman. So this is linear, and I can just split it into a geostrophic bit and an Ekman bit. So there's my Ekman bit, and here are my Ekman equations written in component form. And there's a natural length scale that pops out of it. A is meters squared per second, and F is per second. So A over F is meters squared. You take the square root, that's a vertical scale. It works out nicer with a factor of 2 added. And you can see if I take 2 Z derivatives of this equation, I'll have 4 derivatives here and 2 here, but 2 derivatives of U is just back to V. And so it's a 4th order equation, and I get 4 integration constants. And there are other ways to solve it, of course. But so you have 4 integration constants, 2 of them, and the solution is just exponentials times sines and cosines. 2 of the integration constants are associated with exponentials that decay upward, and 2 are associated with exponentials that decay downward. So if Z equals 0 is my surface, I would use this one for the ocean, and this one for the atmosphere. So if we're teaching this in class, classroom setting to meteorologists, well, we'll say, well, at the bottom of the boundary layer, there is a no-slip boundary condition. So the total velocity goes to 0, which means that the Ekman velocity has to equal minus the geostrophic velocity. So if I'm in the atmosphere, I'm using this one because I want it to decay upward. And if I evaluate it at Z equals 0, well, this stuff is 1, and this stuff is 1, and that's 0. So I have U is C1, and V Ekman is C2. But U Ekman has to be minus U geostrophic, and V Ekman has to be minus V geostrophic. And so that sets these constants, and I just get a velocity that spirals and decays with height and winds up being the geostrophic velocity high above the ground. Okay. If we're teaching it to oceanographers, we say, well, we don't really trust this constant eddy viscosity. Maybe the eddy viscosity depends on Z. So we'll rewrite the equations like this with the A inside this derivative. So this is the flux, and this is the divergence of the flux. And we'll just say, well, we don't really care about the vertical structure of the spiral, so let me just integrate through it from below the Ekman layer to the surface. And if I integrate, here I'm integrating a perfect differential, and so that's a stress that I'm just going to apply at the top, and I assume that it peters out or goes to 0 far below. So I wind up with F cross the Ekman transport, so meters squared per second, is just the stress at the top. So I wound up with this equation. And of course, Z hat cross U is just minus U. And so if I do that and rewrite it, I get that U goes like tau cross Z hat over rho naught F. So people were talking about various vectors like this and calling this something like tau perpendicular to a tau rotated 90 degrees. And it's a convenient thing to keep in mind in meteorology and oceanography that the divergence of a 2D vector that's been rotated 90 degrees is the same thing as the curl, the vertical component of the curl of the same vector. So the divergence of my Ekman transport goes like the curl, and then there's an additional term if this F depends on Y. So I would get a beta term here. And this is just to say that it works, right? So it's a simple theory. This is ocean color. This is a large-scale picture of the wind stress curl that I just sort of pilfered off the web. And so orange in the northern hemisphere corresponds to cyclonic forcing or upwelling, and blue corresponds to anticyclonic forcing or downwelling. And so you get phytoplankton where there's upwelling because the upwelling brings nutrients into the euphotic zone, and that sort of fuels the biology. And then you have these regions where there's not a lot of biological activity in the mid-latitude anticyclonic gyres. And then the color scheme's just reversed in the southern hemisphere, so you get lots of biology here. Notice someone, I think, was talking about a coastal upwelling regime around here. And that's just, if the winds are blowing along the shore, they'll be in the northern hemisphere an offshore Ekman transport, and therefore an onshore circulation kind of coming from below that's bringing cold water. So the waters here would be relatively cold, but like biologically active. So, California's got cold water and sharks, right? And then near the equator, there's also equatorial upwelling. You might naively think that it just comes from this term. But if you imagine just a constant wind stress blowing from the east to the west, kind of like the trade winds across the equator, might have zero curl, this would predict an infinite downwelling at the equator, whereas in fact you get an upwelling. It's just because the Ekman theory breaks down altogether. It tells you that there's a singularity, but gives you the wrong sign. But if you trust it a few degrees off to the north or south, well then an easterly wind blowing towards the west gives you an poleward Ekman transport, and similarly in this hemisphere, and so you get an upwelling. Okay, so let's see. This is just a little tidbit that I'm adding. I was interested in angular momentum balances at one point, and you can interpret the Ekman balance for an eastward wind stress as eliciting a meridional transport of planetary angular momentum. So the angular momentum just associated with the solid body rotation of the Earth. So just the moment arm times the once a day for the angular velocity. So the torque is a force times the moment arm. R is the radius of the Earth, and tau goes like minus V Ekman. And then I just write the F as a 2 omega sine theta. And I can think of, if I think of the angular momentum as just omega r squared cosine squared theta, so the solid body angular momentum, the derivative of this with respect to theta gives me this 2 cosine sine structure. And so all this is, the torque is just equal to V Ekman over R times d by d, so just basically V Ekman times d by dy of this planetary angular momentum. So that's just a cute result that I came up at one point. Okay, so how do we get tau? Well, so I'm an oceanographer, and we call it the wind stress, so we just ask meteorologists what tau is, okay? And well, so what does the meteorologist do? Well, if they're believing the linear theory, well, here's the Ekman solution. And tau is just the vertical derivative. If you take a derivative of these terms, you're just going to get a minus 1 over d times minus u and v, so that's just this term. And then when I take derivatives of the sines and cosines and evaluate them at z equals 0, these will be 0 and these will be 1. And I get, again, this a over d, but times a vector rotated 90 degrees to the left. So the stress is at a 45-degree angle to the geostrophic winds. And fine, you get a value and an angle for the stress, but nobody really is very happy with it because it all depends on A, and A is just something that we made up, right, to get a simple problem. But this is sort of, I've just put this because it sort of speaks to the culture of the atmosphere and ocean communities. You know, the meteorologists are sort of solving the Dirichlet problem, and the ocean community is thinking of the stress as something that we know and we're applying. So that's something that I'm going to come back to. We can do a little better than linear theory if we go to boundary layer turbulence. I'm going back to the 60s. A paper I enjoyed was Blackendar and Tenikis. A little bit of jargon, there's something called the roughness length scale. So this is, we get a log boundary layer and there's an integration constant, and that's called Z naught. And it has units of height, right? But it's, and it's related to the roughness of the surface. So a hilly surface would have a larger Z naught than, say, an ocean or the plains. But the numbers are like centimeters. They're not like the root mean square of the hill size. And U star is a friction velocity. So we're writing tau. So U star bold means a vector, and it's pointing in the direction of the stress. And the stress is taken to be is a quadratic of this friction velocity. And so there are two vertical scales that are important. One is Z naught, which again is just characterizes the surface. And the other one is, well, U star over F gives you a height scale. And so the boundary layer turbulence uses something called singular perturbation theory, and it infers U over U star to be both a function of Z normalized by Z naught and Z normalized by H. So it's a function of two different variables in a sense. And we require that the two solutions match. So as Z over Z naught goes to infinity or Z over H goes to 0, we should get the same answer. And that leads to this equation here. So we have U over U star is a function of Z over Z naught. U here is in the direction of the friction velocity. So V star is 0. And then for the other one, that's a function of Z over H, where we have a U over U star and a V over V star. And these things go to 0 high up, so we get the geostrophic velocities high above the ground. And playing around with the singular perturbation theory, you get a function of one variable and a function of the other variable, and they're equal. So it's kind of like separation of variables, so they're equal to a constant. And this implicit relationship comes out of it. So here, G is the geostrophic velocity relative to the surface velocity. So it's just the amplitude, and similarly, U star is an amplitude. And I have the Z naught, and you can't really solve this. A and B are integration constants that come from these two functions. And they're universal constants, so once you know them, if you change the surface or whatnot, they're the same constant. And you also get a turning angle, which is related to U star over G. So to solve this, you just solve it numerically, right? You just plot the left-hand side, plot the right-hand side, and sort of see where they cross. And it's easy enough to do, and you get kind of a dull solution. So this axis is G, going from 0 to 25 meters a second. And this is U star going from 0 to, 80 centimeters a second. And you'd be forgiven for just saying that looks close enough to a line to just say it's linear and be done with it. So, phi is a turning angle. It's just given by the slope of this line. And it works out to be around 22 degrees for the values of A and B and Z naught that people normally talk about. And it also gives us that tau, U star is proportional to G, but G is rotated through an angle phi. So I can write tau as, U star, the quadratic function of U star, or a quadratic function of G. It's just that this G has been rotated. And my CD then is just also given by the slope of this line, or actually CD is the square root of the slope of this line. Okay, so that's one way, that's where the quadratic drag law comes from. Here I'm writing it as a function of the geostrophic velocity, but it's more common to write it in terms of the 10-meter winds, and you can get that just from, well, U over U star is this function of Z over Z naught, and that works out to be a natural log. And so U near the ground, or at 10 meters, is just whatever it is at the surface, plus U star times a collection of terms that goes like log of 10 over Z naught. So this stuff, the log and the divided by K, becomes our CD, right, our drag coefficient, and I can write tau as a function, a quadratic function of the 10-meter winds relative to the surface velocity. And so when I was taking classes and stuff, we never bothered with this. We just said it was, this was so small, this is maybe 6 or so meters a second, and this is tens of centimeters a second. So we just approximated it like that and took tau to be a given function of the atmosphere. And of course, you could do all kinds of corrections to this with sea surface temperature and CDs that vary with Z naught, which might vary with wave height and so forth. The sea surface temperature comes into play because, if the water's hot on the ocean, it's going to destabilize the atmosphere and change the boundary layer turbulence. So this theory that I've presented is for a neutral boundary layer. So I'm getting to the end of the kind of pedagogical stuff. This is back in the early 2000s, I guess, from scatterometer plots. And the first time I saw this was around 2002. And it's a plot. Scatterometers measure the sort of ripples that are capillary waves on the surface respond directly to the stress, and somehow you can see that from space. And it gives you a direct measure of the stress, and what's plotted is the curl of the stress. And you see this dipolar structure across the Gulf Stream, right? So if you think about a current such as the Gulf Stream, well, one side, there's a maximum velocity in the middle and minimum on the edge. So there's going to be an anticyclonic vorticity on the southern side and a cyclonic on the other side. And this curl is the opposite. It's cyclonic on the anticyclonic side and anticyclonic on the cyclonic side. So it's clearly a dissipation effect. And Dewar, who was supposed to be here, actually was talking about this as early as 1987. But in earlier works, including my own, we modeled this just using this quadratic drag law based on U10. And we just took U10 as an oceanographer. We just took U10 to figure, well, that's a meteorological quantity. And I just took it such that if U ocean were 0, I got a sensible atmospheric wind stress. So this is work that I did with Thomas Duot, who was a student years ago. He's now in Toulouse. But we just ran a QG model. There's a kind of standard problem in oceanography called the double gyre problem, where you just have a box ocean forced with winds that blow from the east to the west here, and the west to the east here, and east to the west there. So just a sinusoidal structure in the winds, and you can kind of see a wave number 1 upwelling here and dark downwelling here. But what's plotted is the curl of this ocean velocity dependent wind stress, and you see clearly this dipolar structure around the model Gulf Stream extension. And again, its sign is opposite the sign of the vorticity in the current, so it's going to be a damping effect. So here we specified U10. We specified U10 such that to get a double gyre forcing if we ignored this ocean velocity dependence. Well, okay, so first I want to split tau into kind of a base part and a correction part, and I'm assuming U surface, the ocean velocity is small compared to U10. So to linearize U10 minus U surface, well, you know, U10's the zeroth order term and U surface is the correction. The linearization of the absolute value only involves the component of U surface that's parallel to U10, right? The other component just rotates it. It doesn't change the absolute value. So I can write tau as basically in my case, just a double gyre forcing here, plus a part that kind of like a drag, but it's not acting on U per se. It's acting on a sort of modified version of U, where I take U tilde as just U plus, basically I count the component of U surface that's parallel to the wind twice. So if the wind's blowing in the east-west direction, U tilde would just be 2 times U x hat plus V y hat, right? And so my U surface dot tau base is going to put energy in at large scales because tau base is a large scale structure. It varies on atmospheric scales. So it's going to put energy in at large scales. And this is going to work out to remove energy at small scales because U dot, this thing, is going to be negative definite. You can do a little bit of scale analysis and conclude that U surface dot tau, U ocean, if you will, dot tau B, scales like this sphere-drift velocity, the sort of large scale, you know, few centimeters a second scale velocity going around the gyre times tau base. And the correction term is, well, it's the eddy velocity times it's the energy containing part of the flow that goes like this. So I have tau C over tau B goes like U eddy over U10, you know, a small number over a big number. But I'm multiplying that by a big number over a small number here. So I get a sort of medium-sized number. And I find that this correction to the wind energy input is on the order of 20 or 30%. So it's just a time series of energy for a standard circulation where I only use tau base and with the ocean velocity dependence, and you see that it's down by a fact, the energy, it saturates at a level about 30% below. The one in between, we did a twin experiment where we had running 2 models simultaneously with ocean velocity dependence, but we used the eddy field from the first model to get tau and use that to force the second model. And you can see you don't get quite as much, or you don't get nearly as much of this damping effect. And the reason, of course, is just because in the twin experiment, the chaos says they'll diverge, and so the eddies aren't in the right place. And so, the mean currents might be in the right place, so it gets that, but it doesn't get the eddies in the right place. So that's what that is. So back to sort of a little bit more modern times, eddy, the oceanographers love cute names for things, and they came up with eddy killing to represent the idea that, well, people are running ocean-only models and going to atmospheric reanalysis data sets to get the 10-meter wind field. And they use it and plug it into parameterizations like this for the wind stress, and find that it takes too much energy out, basically. So it just kills the eddies, and there's too much damping, too much of this top friction. And the reason for it is that U10 itself has an ocean velocity signature in it, right? So we were thinking of U10 as being mainly an atmospheric variable, but it kind of has to in a way, because how do you get U10? Well, it's just U surface, which clearly has an ocean velocity part, plus U star, and U star has this ocean velocity dependence in it. And so, of course, U10 has an ocean velocity dependence in it. In fact, that's why we have to subtract U10 minus U surface in our quadratic law, because we want this, right? So that's, so it's important to use the same U surface in the model simulations that was used in the reanalysis data set, but if you're running an ocean-only experiment, well, you can't, right? Because the data set was just done by meteorologists with a different ocean, or maybe they didn't use ocean eddies, ocean current velocities at all. And so this is called the current feedback effect. And Renaud et al. Proposed a sort of they came up with a sort of a hack, if you will, or an empirical solution. They just take tau to be this tau base that I talked about, and they'll try to get the U10 that they use for tau base they'll try to filter out the ocean part of it. Mine is just a constant times U, and then they fit this, not a constant, but a function of U10. So this is a parameterization that seems to work, and that's standard in models like NEMO now. And I saw this and I just thought, well, fine, but it's the practical aspect, I guess, of the theoretical and practical GFD. But I thought they were giving up on the theory a little too early. And so that brings me to this work with Victorine. So we saw this a year or so ago, and I went back to the formulation based on the UG atmosphere, so the geostrophic velocity in the atmosphere minus the surface velocity. And I just thought, well, this same theory should apply both on the above the surface and below the surface, right? So, I mean, I have tau as rho atmosphere times CD times, UGA minus U surface, and the same thing rotated through an angle phi. But I can say the same thing, there's a U surface and a U geostrophic in the ocean, and apply the same logic. So what people have normally done is just assume U surface is just U of the top grid point of some ocean model, right? The surface, the surface is the ocean, and so it's just the top grid point of the ocean. And we're sort of imagining a rigid lid separating the two fluids. So it's sort of a deformable, rigid in the vertical, but deformable in the horizontal. And U surface is just the velocity of the lid. And you have to solve for it. And you solve for it by equating these two prescriptions of tau. And so what you get then is just that, well, the only difference is the rows here, right? It's the same roughness length. And if we're just really taking this relationship to be linear, the CDs are the same. And I get that U surface is just, well, a ratio, the square root of the ratio of the densities times the geostrophic velocity plus the ocean velocity. So U surface is then not just the top grid point of the ocean. So we're just trying to get a more kind of equitable, treating the two fluids as equals, if you will. And we find that U surface is a weighted sum of the atmosphere and ocean geostrophic velocities. So we did more QG simulations. So using I think it's a 4-layer double gyre problem again. I sort of milked the double gyre problem through my whole career. So I'm just using this prescription of tau, and I've been signed out. And so we tried to mimic, if you will, some of the problems that might arise from using, from getting U10 from some reanalysis data set. So we'll do a truth simulation where, U surface is what our theory says it should be. You might imagine someone doing the reanalysis who doesn't have any information about the ocean current, but knows there's an Ekman layer there, so to speak, and so knows that it's not really no slip at the bottom, it's some sort of partial slip, and so there is a velocity at the bottom just given by this epsilon, the ratio of the two densities, the square root of that, times UGA. One where you just use it, maybe the reanalysis was done just assuming using the same boundary layer scheme that you use over land. And then this is one where you might have some sort of a mean structure of the ocean currents, but not the actual eddies on a particular day. And so we're just going to do that with these different winds, and the same, we'll specify UGA. So the difference from the work that I did with Thomas, we were specifying U10 as a smooth function. Here we're specifying the geostrophic velocities to be a smooth function. And we'll mess up the U10s in different ways. So the U star here would just be calculated, taking one of these surface velocities, and knowing the geostrophic winds is enough to get U star. And so we ran these different simulations, so truth and 1, 2, 3, and 4. So these are transverse spectra. So I'm just plotting kind of U dot tau, but in spectral space. So the Fourier transform of U times the complex conjugate of the Fourier transform of tau x plus the Fourier transform of V times the complex conjugate of the Fourier transform of tau y, and then the real part of all that. So it's just a spectral view of the energy input, if it's positive, or the energy being taken out of it if it's negative. So I'm plotting this on a log linear axis. So I've multiplied the y-axis by k, by the wave number. And that just gives you that the area under the curve, or above the curve here and below the curve here, corresponds to the amount of energy being put in or taken out, right? Because a delta log k is kind of 1 over k delta k, right? So I multiplied by k. So it's just a trick to make the graph look prettier. And you see a little bit of difference at large scales. And the truth one, I'm getting a lot less of this eddy killing than these other ones, right? And this is down here is just this bit of the curve turned upside down for some reason and magnified. So the figures show that this transfer spectrum were normalized such that the area under curve corresponds to the amount of energy added or removed. And we're putting energy in at large scales, and we're taking it out in the mesoscale. And bottom friction is also taking energy out in the mesoscale. So we heard a little bit about geostrophic turbulence and inverse energy cascades. And there's an inverse energy cascade of kinetic energy in the barotropic mode, but the cascades of geostrophic energy are forward, right? They're throughout wave number space because they're forced at the largest scales, at least in the ocean problem. So that's just a side point, maybe a somewhat pedantic point that I wanted to make. So anyway, so that, people talk about this eddy killing, and in the literature they'll say, well, this is the atmosphere, this is a sink of energy, so it's the atmosphere taking energy out of the ocean. And they're talking about, well, it must be a source for the atmosphere, right? But I'll just point out that the energy source or sink for the atmosphere would be, for the geostrophic circulation, would be U geostrophic atmosphere dot tau, right? The air-sea energy flux between the two would be U surface dot tau, and this is U ocean geostrophic dot tau. So this is telling you energy going into or out of the geostrophic circulation. If I plotted U surface dot tau, I would get a much bigger number, like by a factor of 10 or so, 10 or 20. And if I plotted U geostrophic atmosphere dot tau, I'd get a bigger number still. So the main thing the boundary layer is doing is dissipating energy from the atmosphere. About 5 to 10% of that goes into the ocean. Most of that's dissipated in the Ekman layer, and a little bit of it goes into the geostrophic circulation, and some of it's coming back out of it there. And this is just some plots. This is the curl for one of our simulations, one of Victorine's simulations, the curl of U surface, the curl of U10. So U surface, again, is that it's the that weighted sum of the atmospheric velocity and the ocean velocity, but the atmospheric velocity is huge, right? Or has large length scales, I mean, so it has a, when you take the curl, you're dividing by the length scale, so you don't barely see it. U10 is, well, U surface plus something that goes like U star, but U star is kind of negatively correlated with U surface. So this is a little bit weaker version, and then you start to see the wave number 1 forcing. And then this is the difference, and you see the signs flipped when I take the difference. So this is proportional to U star in my truth simulation. And the reason these, when I messed up the boundary layer, when I messed up U10, I get too much. It's just, you know, if I'm subtracting this, but I didn't add it in the first place, I'm going to get a much stronger signal here and a much more, these would be much more saturated colors, right? And I would get a much stronger damping effect. Okay, well, this is plotting U star. Before we said this is just a line. Well, if you look carefully, it's not, right? If I plot the ratio U star over G, if I plot the slope, it's kind of, it looks like this. This is G here, and the slope U star over G here. And then I could worry about, well, should CD really be the same in the atmosphere and ocean? Because my G for the atmosphere is much bigger than my G for the ocean, or the U stars, if you will, are different because one is this ratio of the densities, the square root of the ratio of the densities times the other. So for the ocean, if I just take, I'm showing sine phi in blue for the ocean and red for the atmosphere. The blue one is just a stretched version of this line. Remember, I had this number here. This ratio was 0.035, and 1 over that's, I think, about 28. So I just took this same curve and stretched it by a factor of 28, and that's the blue. So it's not a constant, so maybe you shouldn't use a constant CD. But if you did, you should use a different CD in the 2 layers. And so we've played around with that, and you could even make it different depending on G and so forth. So we played around with that a little bit, and you can see it, but you know, it affects the solution, but not in any way that's worth calling your attention to or that we've digested yet. So this is my last slide. So just to sum up this part of the project or the talk, so for more realistic modeling, I mean, if you're doing an atmospheric boundary layer, or maybe a more realistic simulation over the ocean, maybe think about the boundary conditions, right? Because you know, no slip doesn't really make sense, even if there are no ocean currents other than the Ekman current. You know, some sort of a partial slip, maybe with a rotated angle or something like that, might be more appropriate. This parameterization of Renault et al. Is, you know, seems to work if you just want a sensible model that gives you reasonable eddy field and so forth. But I claim it should really be my U tilde instead of U. So, you know, counting the component of velocity parallel to the winds twice. Well, there are all sorts of other issues. There's sea surface temperature. Well, you know, warm water destabilizes the atmosphere, but it stabilizes the ocean. So there's an effect there, right? You know, if it's destabilizing one, it's stabilizing the other. So there's kind of a, that changes the way sea surface temperature might come into it. And of course, waves open all sorts of cans of worms. So my 3 minutes is about up, so I just got a warning. So I'll stop there, I guess. So thank you.
All right, we have 1 or 2 questions to go, and then we maybe keep going the discussion during the coffee break too, and discussion and break.
It's already coffee break.
Yeah, just a simple question. What you said that the U10 is inherently connected to our ocean velocities? So I didn't get that.
Right, so I mean, that's seen in measurements of U10 apparently, but I mean, of course it is, right? Well, the boundary layer turbulence theory tells you that there's a log layer, right? So du dz, u increases logarithmically in the boundary layer, at least according to this 1960s theory. And it starts out at u surface, right? It's not starting at 0, it's starting at whatever u surface is, which I'm claiming is a weighted sum of the ocean and atmosphere velocities. But so right at the ground, just above the layer, well, it's going at the same speed as the ocean, right? And as you go up, that's kind of decreasing because the U star is anti-correlated with U ocean, right? So in fact, that might give a way to, in a way, you kind of want to, for this kind of modeling, you want to remove the ocean dependence from U10 such that it's an atmosphere-only variable. You might do just a spatial filtering, but I mean, the atmosphere does have fronts and stuff, so there might be small horizontal scales that are truly atmospheric in some sense. But you would expect the ocean bit to decay with height to some extent. And you could use some of these ideas, we're talking about machine learning this week, or to kind of try to extract that and do that. But yes, that's the whole problem with this eddy killing is the people have applied the U10 thinking of it as an atmospheric variable, and it's not, right? It's part of a coupled boundary layer.
Okay, thank you.
You didn't discuss much what this stress on the ocean really is. Is it like a stress between two plates, or what kind of physical processes are involved?
Well, okay. There's a poster by Bella, I don't know if she's here, but who talks about it a little bit more, the boundary layer turbulence, but in more detail than I am. But the stress is just, it's just the eddy transport, so the small scale turbulent eddy transport of vertical transport of horizontal momentum, right? So it's just what I'm calling the stress is the atmosphere to ocean flux, vertical flux, so from the atmosphere to the ocean of horizontal momentum. And as you've pointed out to me, some of that goes into the wave field, right? So to really do this correctly, I'd have to figure out how much goes into the wave field, and I don't really want to equate the stresses, but I want to just equate the stresses of these two turbulent boundary layers. Right? That makes sense, I'm not sure. But
okay, maybe just one more question and then let's go for the coffee break.
The eddy killing process that you described, up to what scale of eddies do you think it will be affected? Would it stay at 100 kilometers or would it extend to 10 kilometers?
No. So it's all scales, right? So the only
But is
reason
it
people
equally felt at all scales? There has
sure,
to be
it's active at all scales. People call it eddy killing just because it's kind of proportional to, in some sense, to the kinetic energy, and the kinetic energy is all in the mesoscale, or well, all. I mean, but so when I call it eddy killing, I mean, it acts on the mean current too, right? It acts on the currents and the eddies, and even the Sverdrup circulation is just, it's trivial for the Sverdrup, so it's a small term there because most of the the term depends on. Let's see if I can find it, but I don't know if it's. I guess it's this, right? So it's what I'm calling eddy killing. This is a stress, right? So work is force times distance, right? So rate of working is u dot force, right? So this is a force at the surface, okay? And it goes like minus, the tilde is a complication, but it goes like minus u ocean, right? So U ocean dot U ocean is U ocean squared, right? So it's the kinetic energy, and it's minus the kinetic energy. Well, not exactly, because there's this U10 is variable, but, so people call it eddy killing because most of the kinetic energy is in the mesoscale eddies.
Thank you.